Start.
Good afternoon, everyone. This is Group 19 of the Department of Computer Science at Makerere University and congested. So we have over 3 million plus population. We have an over 3 million plus population in Kampala. So this is a disadvantage because the population cannot sustain, the growing population cannot sustain the available infrastructure. So we noticed that there is a heavy congestion, for example, here in Kampala, Wandegea intersection. At peak hours, we find that, okay, when there's a lot of working around, like in the afternoon, you find that peak hours is jam of these 1,400 cars or vehicles in an intersection, all of them wanting to use the intersection. And this causes a congestion that leads to a loss to the city of around $380,000. And the intersection that we have here, it runs in a loop of 92 seconds, which is a fixed cycle. It cannot adapt to the increasing population, and they cannot adapt to this kind of movement. So then we have the private vehicles that take up 25%, the minibuses 20%, and then the trucks 5%. Next slide. So the major problem is the 92-second, the problems that we are facing, the 92-second fixed cycle where the signal runs in a fixed loop, and it doesn't cater for the growing traffic. Then we have the zero lane discipline where borders just use whichever path they take, and the available research papers, the reinforcement learning is actually focused on the Western side and the Asian countries where people follow a traffic code like this that has been made. Then the city loses around $380 per day. $80,000 per day. Next slide. So our objectives our objective was to build a calibrated sumo micro simulation. This simulation was we were focusing on trying to compare it with the available fixed baseline, like the available fixed time mechanism that is at the intersection. Yeah. And we are using the LHT network together with the vehicle types we are putting into consideration. The LHT network helps us to simulate the infrastructure, the lanes, and how the lanes are built, like how they are constructed. So with that, we were able to implement PressLite, the two algorithms that have been made to cater for traffic within lanes, so at intersections. So implement PressLite that focuses on the pressure. The pressure will mean the queue lengths. They then implement IntelliLite. This focuses on the spatial temporal, that is the specific positions of cars and the time and their time, the throughput, the intersection. Then we have then we trained and tested across low, medium, and peak demands. Then we also did the statistical validation where ANOVA is the analysis and validation, which focuses on is there a difference between what we are implementing and what is already there. Then the Tukey HSD, which is the honestly significant difference. This focuses on the where the difference is, yeah. And then the Cohen's D, this one focuses on how big the difference is between the low, medium, and peak based on what is already there and what we are implementing. Let me go on to the next presenter, take us through the next part.
We had about 6 phases. The first was a collection of data, and we did this using SCA reports, UNRA reports, also the Google Traffic API. And then we also had to process this data. This involved us normalizing the flows, deriving proportions, and things of that sort. Then we had the Sumo simulation setup. We used the LHT network, and then we did sublane models, then also set the vehicle types. Then we had to set up the reinforcement learning environment involving Tracy, the Tracy interface, and all of that stuff. Then we also worked on the models. This was the PressLite model, then the IntelliLite model. Then we did the evaluation of these models and the statistics. We used ANOVA for NSD, among other things. For the Markov's decision processes, we had fields like the state, we also had the actions and the rewards. And this included, well, for the states, this involved things like traffic measurements, pressures, and also lane features concerning each respective reinforcement learning algorithm. And then we also had the actions, which were discrete actions. This just basically decided how each model would choose the green phase for each arm. And then we also had the rewards, and this was basically just negative phase pressure and also multi-objective rewards for IntelliLight algorithm specifically. Then we had the gamma. Gamma was acting as our gamma was up. Was. Yes, gamma was acting as our discount factor, and we set this at 0.95. We also had about 10 seconds for the green light, 3 seconds for each yellow transition, and the entire process took about 30 training episodes, which would convert to about 30 hours. Next slide. So for the simulation, we had to set up the Wandegear junction. And for this, we used the two inbound and two outbound lanes per arm. We had Bombo Road, which was running north to south, and then Ferry Hill Road, which was running east to west. The signals each had 8 phases, and then we had sublanes in each lane, then the high or peak scenarios. And for each of these, we had about 400, 800, and 1400 vehicles per hour, respectively. Next slide. So we had 2 algorithms that we worked with. We had the Press Light algorithm and then the IntelliLight algorithm. We got these from 2 papers, both of which were written by me and others. One published in 2019 and the other published in 2018. We used 2 state vectors, one with 12-dimensional pressure, was a 12-dimensional pressure vector. That was what we used for the Press Light algorithm, and then a 39-dimensional vector was for the IntelliLight. The IntelliLight had more dimensions because it takes in way more data than the Press Light. We are basically using spatial temporal mapping here, while we were just using maximum pressure for the Press Light. For the reward functions, we used the negative phase pressures, and then for the IntelliLight, we used multi-objective metrics. And then we had to set up the networks using about 764 parameters for the Press Light, and then over 9,000 parameters for the IntelliLight. Then concerning the optimizers and the insights, well, as you can see, for the insights, we had reactive and the Press Light algorithms were reactive and responsive to, current pressures. And then for the IntelliLight algorithm, it was majorly proactive because it would sort of forecast what would be going to happen and then be able to reduce the traffic for that particular lane. On to the next slide. So concerning the training and the evaluation, we employed 30 training episodes. This would translate to about 3,600 seconds, which is about 30 hours of training. And these 3 major known scenarios, that is low, medium, and high, or peak scenarios. And then we had 4 controllers that we compared. So the controllers were the fixed time baseline. And then we had the maximum pressure algorithm. Then this was without the deep Q learning. Then Press Light involves the deep Q learning on the maximum pressure algorithm. Then we lastly had the IntelliLight DQN. So As you can see, we have the states for each. For the max pressure and press light, we had 12 dimensions, and for the intellect, we had 39 dimensions. Give for the parameters, we had 764, 9,224, then press light and intellect respectively. Then for the training, fixed time, press light did not require training, and the maximum pressure also did not require training. But the other two, we trained them for 30 episodes each. On to the next slide.
Normal fixed time lights, fixed time baseline results using the 92-second wait. So for low traffic, which is 400 vehicles per hour, those vehicles waited in the queues for about 13 seconds, for about 364 seconds, and there were 13 vehicles which were queued at every interval. So now the difference between the low, medium, and high pressure were 13, 21, and 25 seconds, 13, 21, and 25 vehicles rather, with the seconds increasing with every increase in the level. So at peak, only 60 vehicles were cleared in the 92-second window, and those 60 vehicles rather, make up for less than 12% of the 1,400 arriving. And this was a very horrible measure for peak traffic hours at the junction. So our first algorithm, which is the press light deep queue network, reduced the queues by 98% for low pressure, which was around, I go back it was around 400 vehicles per hour. Yeah. It reduced it by 98% for the low, it reduced it by, and can move on smoothly. And so basically it failed to account for that. That's why the 1.9% shows how low its performance was for the peak pressure. In contrast, IntelliLight's results were very, very promising, with 98.7%, 95.5%, and 96.1% showing the queue reduction for low, medium, and was a better one to use, showing better results of 18, 68, and 101 for the different pressures. All controllers at peak scenario. So now this bar graph shows the controllers, fixed time, max pressure, press light deep queue network, plus the IntelliLight at the peak scenario, which is 1,000 vehicles every hour. IntelliLight, the queue reduction was 96.1%. So only one vehicle was in the queue at peak. And then for press light deep queue network, for max pressure, for fixed time, you can see that press light and fixed time could not handle the number of cars which were in the queues. So that is a testament to how our press light deep queue network would actually helped in the traffic reduction for the simulated urban mobility. And I think I'll hand over to my colleague to handle the rest.
Good afternoon. I'm going to take you through the statistical validation. So we didn't just report numbers, we validated everything, every finding with rigorous statistical data. So looking at the ANOVA table, in all three scenarios, low, medium, and peak, the statistic is large, the F statistic is large, and the p-value is below 0.001. Statistically, it's a failure which is statistically confirmed. And then finally the Cohen's D, it measures practical effect size. Above 0.8 is considered large, and IntelliLight at its peak achieves its D at 5.73, and Presslight at its peak achieves 0.005, which is negligible. Next slide. So the 6 takeaways from this project: the state richness. Sorry, where is first pause Chida? Okay, continue. The 6 takeaways from this project: one is the state richness wins. A 39-dimensional state capturing waiting time, and speed is fundamentally more powerful than a 12-dimensional pressure vector under saturation. And then 2, proactive beats reactive. Detecting Q buildup before lens even overflow is the decisive advantage IntelliLight has over Presslight. Then 3, saturation breaks Presslight. The pressure signal flattens when every lane is full, which removes the learning gradient entirely. So that is a fundamental algorithmic limitation. The number 4, the analytical max pressure controller requires zero training, and it gives a 47.8 reduction. And this could possibly be deployed at 1 gigahertz today using all the results are simulation based. We have not deployed anything at the physical intersection, and the gap between simulation and reality may affect how trained policies transfer. The second one, single intersection, Presslight's coordination benefits across multiple intersections. They were not tested here. It's just the design strength. And then the 3D training episode, 30 training episodes may not be enough for full convergence at peak saturation. Presslight's failure could be partly a training duration issue, not purely algorithmic. And then no pedestrians are modeled. There are no pedestrians that were modeled despite being significant near at Makerere University. Yeah, so for the future work, the most valuable next steps are extending to Mulago and Boise Junction, adding Sumo's emissions model, investigating transfer, learning to the physical intersection, evaluating newer algorithms like the MP light, the core light, and validating against real KCCA loop detector data. Now, next slide. So in conclusion, the IntelliLight's Q reduction across all demand levels is consistent, and approximately 100% reduction in waiting time. This is eliminated in practice, and then there is an increase, a positive 68%. It shows an improvement in peak throughput versus the current fixed time plan. Then you can see there's zero training required for max pressure. So you can apply it. It is practical. You don't need to anything else. You can literally just apply it right now. Yeah.